Good morning. Today we are going to study about binding energy. We already know what is a binding energy and we had studied it in the plus 2 classes. So in this class we are trying to recollect all the things which we had studied in our lower classes. Starting from the famous mass energy relation, that is E equal to mc square, derived by Albert Einstein in special theory of relativity. We can calculate the energy equivalent to a mass m by the equation E is equal to mc square. A 1 kilogram mass will have an energy E is equal to 1 into c square, isn't it? So it will give you 9 into 10 raised to 16 joule. That means a 1 kilogram mass has an energy of 9 into 10 raised to 16 joule. The mass associated with an amount of energy E is given by E by c square. How? By taking m is equal to E by c square. So the mass associated with an amount of energy E is equal to E by c square. So Einstein's mass energy relation emphasized on the energy liberated, which is contained in the mass of the ordinary matter. So this mass incorporates energy and this energy is liberated. And he explained about this energy liberation contained in the mass of ordinary matter. So we have the equation E is equal to mc square, isn't it? So we can calculate the energy equivalent of an electron, because we know the mass of an electron is 9.3 into 10 raised to minus 31 kg, isn't it? So we can substitute for the mass of an electron here and can find out the energy equivalent of mass of an electron. And it is obtained as 0.511 MeV. Here the unit is in MeV. Whenever we do the calculation E is equal to mc square, it will give you the result in joule, and that joule can be converted into electron volt by the equation 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. Similarly, you can calculate the mass of the proton also, and it is 938.29 MeV, that is the energy equivalent of mass of a proton. Moving on to the figure. Here we are having a helium nucleus with us, He24, on the left pan, and the nucleons. In a helium nucleus there are 2 protons and 2 neutrons are there. So we have 2 protons and 2 neutrons on the right pan. Which pan will we move? The pan that is having nucleons will weigh more than the stable nucleus, stable helium nucleus. So the mass of the stable nucleus He24 is less than the total mass of its nucleons. So there is a mass difference, isn't it? That mass difference is called mass defect, denoted by delta M. So how we can define mass defect? It is the difference in the mass of a nucleus and its constituents. So the difference in mass of a nucleus and its constituents is called mass defect. Now how we can calculate the mass defect? The mass of the stable nucleus He24 on the left pan is given as small m. Now how we can calculate the total mass on the right pan? There are 2 protons and 2 neutrons on the right pan, isn't it? So how we will calculate the total mass? So there are, in general we can say that there are Z number of protons in a nucleus. So Z into mass of protons plus, how we will calculate the number of neutrons? It is A minus Z. So A minus Z into Mn will give you the mass, total mass of the neutrons. So Zmp plus A minus Z into Mn will give you the total mass of the nucleons and minus M, where M denotes the mass of the stable nucleus. So mass defect is calculated as Z into mass of proton plus A minus Z into mass of neutron minus M. And we had already started our session with the famous mass energy relation, isn't it? That is, a body having mass m will have an energy mg square. So here we had calculated mass defect. Now the energy equivalent to the mass defect of a nucleus is called its binding energy. I repeat, the energy equivalent to the mass defect of a nucleus is called its binding energy. You can see the figure where there is a nucleus and its separated nucleons having greater mass than the stable nucleus. So we can write binding energy as mc square itself. But here m is delta m, the mass defect. So delta m into c square. Sorry, I have forgotten to write the c square there. So Zmp plus A minus Z into Mn minus M into c square must be there. So that is the equation for binding energy. Now what will be binding energy per nucleon? What is the total number of nucleons inside a nucleus? It is denoted by its mass number A, isn't it? So what will be binding energy per nucleon? It will be binding energy divided by A. So binding energy per nucleon is denoted by Be bar, which is equal to binding energy per divided by A, which is, again you can substitute for binding energy as Zmp plus A minus Z into Mn minus M into c square divided by A. So that is the expression for binding energy per nucleon. Next we have binding energy curve. A graph in which binding energy per nucleon is plotted as a function of mass number A for various stable nucleus is called binding energy curve. A plot of binding energy per nucleon as a function of mass number A for various stable nuclides is called a binding energy curve. So here you can see on x-axis we have mass number and on y-axis we have binding energy per nucleon in MeV. And you can see that initially the graph starts increasing and it attains a maximum value at A mass number is equal to 56. After that it goes on decreasing. So this is the binding energy curve, and we are going to study more about this binding energy curve. So the first point is, if the binding energy per nucleon is greater, the nucleus will be more stable, isn't it? So if the nucleus is having more binding energy, nucleons will hold together, isn't it? So the binding energy is related to the stability of the nucleus. So higher the binding energy or higher the binding energy per nucleon, the more stable will be the nucleus. Here you can see in the picture that the maximum binding energy per nucleon is 8.8 MeV per nucleon, and it is for iron with Z26 and A56. So iron is an element having maximum binding energy per nucleon. So it is the most stable nucleus. So the region near iron is called a region of greatest stability, because there you can see a small straight line. So it is having approximately equal to the maximum binding energy per nucleon, that is 8.8 MeV per nucleon. So that is a region of greatest stability. Now the second point, if each nucleon interacted with every nucleon, there would be A-1 interaction for each nucleon. Just think that we have a proton and a neutron. So two nucleons are there. So the mass number will be A equal to 2. And they interact each other, means there is only one interaction between them. So we can generalize and can say that there will be A-1 interaction for each nucleon if each nucleon is interacted with every nucleon. So the binding energy, we can say that the binding energy, since there are A-1 interactions, the binding energy would be proportional to A-1. We can say like that. Or in another way, we can say that there is only fixed number of interactions per nucleon. That is first one, what I had said is a picture in which the nucleons will interact each other, so that the number of interactions will be A-1 and the binding energy will be proportional to A-1. In another picture, we can consider each nucleon is attracted to its nearest neighbors, so that there is only fixed number of interactions per nucleon. And this concept leads to the concept of constant nuclear density. How we can calculate nuclear density? Nuclear density is equal to, how we will calculate density? Mass by volume, isn't it? So we can calculate the nuclear density of any nucleus and can be found out that it is a constant. In another picture, we can think that if binding energy per nucleon is proportional to the number of nucleons, the radius would be approximately a constant. That is, the nuclear radius, we approximate it as 10 raised to minus 15 meter, isn't it? So the radius is approximated as a constant value, where the binding energy per nucleon is proportional to the number of nucleons. Now we had already discussed the region of greatest stability, isn't it? Region of greatest stability is a region where the nucleus is having maximum binding energy per nucleon, that is 8.8 MeV per nucleon. So what happens to all other nuclei? which is outside this region. They will try to reach the region of greatest stability, so that they must be stable. So the region of greatest stability is having more importance because the other nuclei which are far away from this region will try to come towards this region to attain maximum stability. And for other nuclei there are only two options for that. So let's check for it. So we had plotted it with the x-axis as mass number A, isn't it? So consider the region of high mass number. See, there is an example in the picture, that is Au gold with mass number 197, and the maximum stability is attained by the iron with A is equal to 56. So gold is having 197 mass number and iron is having 56 mass number. So what will happen to this gold nucleus? In order to be more stable, the mass number has to be reduced, isn't it? 197 must decrease to 56. So what happens to the nucleus? The nucleus, so it is a heavier nucleus, isn't it? It's having a large mass number. Large mass number means it consists of more number of nucleons inside it. So it's a heavy nucleus. So what happens to this heavy nucleus? This heavy nucleus will split into lighter nuclei with the liberation of energy, and the process is known as nuclear fission. So region of high mass number, for the nucleus to be more stable, mass number has to be decreased by the process called fission, in which a heavier nucleus is splitted into smaller nucleus with the liberation of energy. Now what happens to the nuclei with lower mass number? That means mass number A less than 56. You can see several examples here: hydrogen, helium, lithium, carbon, nitrogen, oxygen, calcium, neon. These are all the examples having mass number A less than 56, isn't it? So what will these nuclei do? They have to increase their mass number so that it will reach approximate to the region of greatest stability. That means it should reach A equal to 56. So what they have to do? They have to join so that their mass number gets increased and they can reach the region of stability. So for the nucleus to be more stable, mass number has to be increased, and that is a process known as nuclear fusion, in which small nuclei combine together to form heavier nucleus with liberation of energy. So in the lower mass number, nuclear fission takes place, and in the higher mass number, in the lower mass number, nuclear fusion takes place, and in higher mass number region, nuclear fission takes place. So that in both the cases, the mass number will change approximate to the mass number of iron, so that these nucleus will attain maximum binding energy per nucleon, or it will be more stable. So that is a peculiarity of this binding energy curve. You have to specify the x-axis and y-axis parameters, and you have to draw the region of greatest stability, also the element having the highest binding energy per nucleon, that is iron 5626, and you have to specify that in the lower mass number area, the nuclei undergoes fusion, and in the higher mass number, the nuclei undergo fission to attain maximum stability. Thank you.